Hello, everyone, and thank you very much for coming to this session about security. Do you still enjoy the conference? I don't hear. I can't hear you. Excellent. And have you had a great time last night at the party? I had a very good time. It was the first conference where I seen a live band and some awesome lyrics, the best ones I've ever seen. So do you think we can still talk a little bit about security after all of this good fun? Let's see. Because the security, when done correctly, is not that difficult, and you are software engineers, pretty smart, problem-solving people by default. So let's see what's all this security about. How many of you implement some sort of application security because you have to comply with some regulations? So I see a few hands. Excellent. And what usually happens, you have a security team that creates a compliance policies that contain some security vulnerabilities that you have to comply with, SQL injection, cross-site scripting, or any other vulnerabilities that your software has to comply with in order to be accepted. And this approach ends us focusing on avoiding these vulnerabilities rather than prevention. The result of this approach is that a high number of insecure applications are still developed today, and injection is still king. In the latest OWASP Top 10, 2017, the injection is still in pole position at #1. So the question is, can we do something else about this? And this is what we are going to explore as part of this session. We will look at these vulnerabilities from a different angle. We would analyze them and decompose them into the security controls that prevent them. And we will flip the focus from focusing on the vulnerabilities which we can measure in the software only at the end, after the software has been already developed, which is way too late, to focus instead on the security controls that we can implement and measure from the beginning. A little bit about myself. My name is Katy Anton, and I come from a software development background, just like yourself. In my previous life, I started from development, and then I went into management, where I created and led teams of developers. And as I was responsible to deliver software, this is when I had to get into application security. And at that moment, I got involved into OWASP Top 10 Proactive Controls project, where I joined as co-leader. Today, I work as application security consultant at Veracode and help developers around the world to secure their software. And in many companies where we have these policies, they contain the so-called CWEs. And what this stands for is for Common Weaknesses Enumeration. It is a list from Mitre, and it is a formal list which is used as a common standard, a common language to define software security weaknesses at architecture, design stage, and in the code. And this is what's all about. So all of these are actually software security weaknesses. And you can see a classification of all of these CWEs, and you can see this one in, let me see, on the NVD database. The NVD stands for National Vulnerability Database, where they have a very nice classification. Let me see if I can actually bring it on. Yep. And here you can actually see a lot of vulnerabilities and what actually they are caused by. And what it is actually, in the end, we have these weaknesses into the software, either at the code or at design or in the architecture. And this is all what's about. Okay. Let me bring my mouse back. The first category that I will explore is the injection, because this is still the most common type of vulnerability which we found in software applications today. The injection as a category, it is a large category. It contains multiple types of injections, and each of them have its own defensive mechanism. So you have command injection, cross-site scripting, code injection, XML injection, LDAP injection, SQL injection, just to name a few injections. And if you go further into classification in each of these, then you have further classification, depending, for example, of the attack mode. So you can have inbound injection, when you have the attack and collecting the results on the same channel, or you can have out-of-band injection, where you can have the attack on one channel and collecting the results on a different channel. So it can be quite overwhelming to think of all of these injections, different type of injections, different type of exploiting them, depending of the channel, while you write the code. And probably this might explain why we still deal with such a large of applications that have various type of injections. So is there anything else that we can do about these large categories? Can we look at it in a different manner? For this, I will go to a very basic definition of what the injection is. The injection occurs when you have input, it doesn't matter where it comes, you have some input, which is then combined with a sort of a syntax. This result is then sent to a parser, and that is when it ends up being executed as code. And the input, which is not only from get and post, but is from a wide variety of sources that can be tainted, file uploads, HTTP headers, you can easily change those in Chrome with developer tools. Any data that sits on server files, configuration files, data from the database, you should never trust your database. All this data from all this variety of sources that is then combined with a sort of a syntax that is sent to the parser. And if we want to store the data to the database, that's going to be sent to the SQL parser. If we want to render a web page, that will be sent to the HTML parser. And that's when we end up with that input, which is executed as part of the code on the output. So that's when we actually end up with the injection. Now, I will take this view because I want to focus more on the output, the red bit, where we end up with the input executed as code. And I'm going to flip it in order to understand on how to prevent it. So in the case of the SQL injection, we have the input, which is combined with the SQL query that is sent to the parser. The best defense for this is to parameterize the data just before sending it to the parser. And this is the primary control. But as defense in that, we still have to validate the data. And it's important to do both of them, because if we do both of them consistently, then we can prevent vulnerabilities that you as developer might not necessarily be aware of. A good example of this is the second order SQL injection. This is the injection where the injection payload stays dormant in the database until it finds the right environment to be exploited. It's also an out-of-band type of injection. When it comes to cross-site scripting, the primary defense for this is to contextually encode the characters before creating that HTML document that is sent to the parser but as defense in that we still have to validate the input. And similarly for XML injection, code injection, LDAP injection, and command injection. So instead of focusing on all these type of injections, which can be overwhelming and definitely is not possible while you write your code, instead we can choose to focus on the security controls that prevent them. And as primary controls, always to parameterize the data, to separate the input from the command before sending it to the parser. When this is not available, like in the case of cross-site scripting or other type of injections, contextually encode that output before sending it to the parser to effectively neutralize the characters that can trigger the injection. But as defense in that we still have to validate the input, this helps to reduce the attack surface if done effectively. The best way to do this is at the point where your data enters your application to effectively reduce the attack surface. In the case of MVC framework, this point is in the controller. So that would be the best place to validate your input. The next type of vulnerabilities issues that I'm going to tackle is intrusion detection, or better said, lack of it. In many applications, high-value transactions logging or fail loggings are not logged. If there is some sort of logging, then the format is not consistent enough in order to allow operations team to centralize all these logs and automatically process, so they can get some information within a reasonable amount of time to detect any suspicious activity. As a result of these two problems, insufficient logging information and inconsistent logging format, there are many applications and APIs out there that are not monitored for suspicious activity. To put it in a very simple terms, if a pen tester is able to get into a system without being detected, it means that the system does not have in place sufficient logging and monitoring. And the question is, can you, as developers, do something about it? For this, there is a control, and this is the security logging. The security logging has been introduced in the OWASP Top 10 proactive controls in 2016, and then in 2017 has been taken over by the OWASP Top 10 team as entry number 10. And let's go to some examples about on how you can actually implement this. According to OWASP App Sensor project, there are 6 types of detection points that are considered good attack identifiers. And these are authentication and authorization failures, client-side validation bypasses, whitelist validation failures, obvious code injection attacks, like for example, obvious SQL injection strings, and the high rate of function use. For example, if you have a high number of page requests in a very short period of time. So let's go a little bit more in detail through some of these examples for you to have a better understanding of what you need to look for. So in the case of a request, if your application expects post, but instead it receives get, this is a very good indication that somebody has intercepted that communication and has intentionally changed from post to get. This anomaly, this type of exception, should be logged. Again, if your application expects extra form or URL parameters, in .NET applications or those frameworks where you have auto-binding, this can lead to mass injection. And also, something that a pen tester will do almost every time he gets his hands on an application is to try, for example, to send an extra parameter like debug equal true. So if your application receives on the server side extra form or URL parameters, this is a good indication of an exception that should be logged. In the case of authentication, if your application expects to receive 2 parameters, the username and password, but instead it receives only one of them, the username, because the password has been removed, this is a very good indication that somebody has intentionally removed that parameter, and this exception must be logged. Similarly, and something that a pen tester would do again, is to add an extra parameter during authentication, admin equal true. Something that they will definitely try to see how your application behaves when they add admin equal true, and he can actually increase the privileges. So if this happens, this is another type of example of an exception that should be logged. In the case of validation, if your application, if the server-side validation fails, despite the fact that you have a client-side validation. A very good example of this is you have a form on the client. The form has, in one of the elements, an HTML attribute of maximum length. However, when the data reaches the server side, the length is greater than the maximum defined on the client side. This is a very good indication that somebody has intentionally intercepted that data since it has left the client and has intentionally changed that string. And this is another type of exception that must be logged. Now, here I just gone through some examples. You can actually go further in detail onto the OWASP App Sensor project detection points. You have the link at the bottom of the slide. And you can have a look at more examples, and you can look at this, how they actually map into the business logic of your application and where you can implement them in your own application. And by putting this into your software, what you are actually doing is you just ensure that the data that you expect to receive is the data that the application receives, and it's in the format that is correct, is expected. However, when this does not happen, by putting in place these exceptions, by logging these exceptions, what you are doing is you are giving your software the mechanisms to respond in real time to these possible identified attacks, the ones that we have identified. And depending on how you choose to code them, you can reduce or even stop them. So if we are to recap the security controls that we have discussed by now, every time our application receives data, not only from user, but also from a wide variety of sources like database configuration files, we must validate it in order to ensure that it is in the right format. When this does not happen, we should log the exceptions in order to give the software the mechanisms to respond to these possible identified attacks. Any output should be contextually encoded, and anytime we store data into the database, we should parameterize the queries. The next category that I will explore is about data exposure. And when we talk about data, it's about data at rest and in transit. Now, when it comes to data at rest, there are 2 types of data. We have data where we need to know the initial value, and this must be encrypted, and like, for example, credit card, and data where we don't need to know the initial value, like, for example, password. This must be hashed. And then we have the data that is transferred, data in transit that must be transferred over a secure channel, encrypted. When it comes to data at rest, can be quite challenging to get it right. And this is an example from an application of a vulnerability at design stage. And during the code review, we have realized that in the same folder, there are two files. One of them, encrypted password, we kind of guessed what the encrypted password contained. The other one, password entities. And when opened, it revealed that it contained acid, assault, and iteration. It turned out that all of these were used in conjunction with the password-based key derivation function 2 to generate the key that was then used for encrypting the data. So, to summarize it, in the same folder, we had the encrypted data and everything that an attacker would need to generate the key to decrypt that data. So happy days for everyone getting access to that server. Definitely something that you should not do. And the reason I choose to give this as an example is because homegrown solutions of storing the keys are very difficult to get them right and very easy to get them wrong. So when it comes to encrypting the data, another example that I want to take you through is the machine keys. And these are available in .NET applications. And these are keys that are used for authentication, CSRF, view state, and password reset token. And some developers, when they implement this, might find it difficult, and then they go like on Stack Overflow, where everyone goes, and then they put their configuration file there, and somebody else answers and puts their configuration file that is working. Which means that at that moment, these keys are publicly disclosed. And this is not just an example. In fact, there are many of them. So many that somebody, like the guys from Not So Secure, have actually created a tool of all of these publicly disclosed keys. So you can use this tool to actually, if you're using these .NET applications, and if you are using machine keys, to see if that key in your application has been publicly disclosed. If you don't do it, an attacker will definitely do it, because these tools are publicly available for everyone. So in the case of encryption, we still have to use a strong cryptographic algorithm like AES, but when it comes to the keys, we must store the keys away from the encrypted data. And because they are secrets, we must protect them in dedicated key vaults. HashiCorp, Amazon, there are quite a few solutions out there. And it's also important to define a key lifecycle and to have in place into the software the ability to replace these keys. We have to remember that if the key has been compromised, then you must replace that key anyway. So it's better to already have in place the process and document the process in order to know exactly what to do when this happens. When it comes to data in transit, we are pretty good today thanks to Let's Encrypt and the efforts from Chrome on encrypting data on public websites. But we still need to do some work on encrypting data between the application, server, and non-browser components, in particular behind the firewalls. So I work with a lot of Red team members, and I know quite a few of them. And their feedback is that after they got into a corporate network, the security controls are minimal, which is scary. So once they are in there, which is not difficult to get, they don't have any obstacles, so they can do a lot of damage. So that's why having this communication over TLS channel makes it more difficult for attackers once they are in the network behind the firewalls. Another category of issues that I will explore is third-party components, or in other words, using software components with known vulnerabilities. According to the State of Software Security Report, 85.7% of .NET applications and 92% of C++ contains at least one component with one known vulnerability. And I work a lot with developers to help them out with this issue. And we are pretty good at identifying the components into the software and the vulnerabilities in those components. And there are open source tools like OWASP Dependency Check, which looks for application .NET and Java, and then searches those libraries against NVD. And you have quite a few commercial applications as well that can give you more for your money. But despite of all of these, and all these pretty reports with pretty colors that we get, the problem that I see is in the time it takes to do something about them, to upgrade them. And the type of software that has these issues is the type of software that no developer wants to touch. It's the type of software you change something in one part of the software and something else breaks in a completely different part. It's very easy to break. And as a result of this is difficult to test. You might have some functional tests, but very limited coverage. And all of these problems means that it's pretty difficult to upgrade, and as a result, it leads to a high level of technical debt. And this is what's all about. We have this type of applications with a lot of vulnerabilities are the type of applications that have high complexity in their applications and have a high level of technical debt. Before we move forward, I want to introduce another term, and this is the attack surface. So in security, we are referring to the attack surface as the sum of all the points through which an attacker can get into a software applications in order to enter data into and extract data from a certain system. And in application security and in security in general, there is a basic principle, and this is whenever we create our applications, we need to ensure that the attack surface is kept at a minimum size. So we need to ensure that our attack surface is as minimum as possible as we can have it. So let's explore three types of components. I will explore an open source library, but I will not focus only on open source components. I will also explore implementing a vendor API, because today there is an increasing trend where rather than actually breaching the target, someone will choose to breach a partner of a target. And also a common case, in particular in large companies, of having a library that has been developed by one team, and then that is reused on multiple applications within the same company. So when implementing, I'm going to choose implementing a login library, which is quite common in many applications. And as many already made libraries, it has a wealth of information, of functionality. And some of it you don't necessarily need for your own software. But the reason I choose a login library is because this is a very good example of a third-party component that touches your software in tens, hundreds, or even thousands of points, depending on how your application, how large is your application. And every time this third-party component touches your software, it means that if there are vulnerabilities in that one, then those can be exposed directly into your software. And if there are ways for the attacker to get into those, like we have seen in the previous talk, then all those hundreds, thousands of points are points where an attacker can actually exploit. So for this type of scenario, when your library is going to be used in many parts of the software, but you need from that library only a subset of the functionality, a good software design for this is a simple wrapper, and in .NET you can use, and for this you can actually use an interface. And by using this, what you are actually doing, you ensure that you expose into your software only the functionality that your software needs, and you hide unwanted behavior. If there is any vulnerability into any of those methods that are hidden, then those are not exposed into your software, and in this way you have actually reduced your attack surface. Having that one point also gives you the point of control where you can add extra security controls if you need to. But also this design pattern helps to replace or even upgrade your libraries without much penalty. The next example that I will consider is an API from a vendor. And for this, a common example is in e-commerce applications to implement a payment gateway. And highly likely that a website will have more than one payment gateway working at the same time. And also there is a common scenario where you have each payment gateway from each vendor will have its own endpoints, its own methods, and your application is highly likely that will have its own transactional methods. So for this scenario where you need to convert from the provided interface to the one that your own software requires, a good design pattern is the adapter design pattern. This also helps to have multiple adaptees working with one adapter at the same time, and you can easily switch between them. And it's a design pattern that helps you that if one of the partners has been breached, then this gives you the control, and you can switch that partner, switch with another vendor. And the last example that I will consider is implementing a library that has been designed by another team within the same company. A very good example for this is the single sign-on. In some cases, this can be quite complex packages. So for this scenario, when you need to bring into your software a complex subsystem, a good design pattern that can be used is the Facade design pattern. This is also good for legacy systems. It helps you because it simplifies the interaction between your own software and complex subsystems and reduce the dependency of outside code. And it gives you that one point, that control, where you can actually apply extra security controls if you need to. So if we are to recap, secure software starts from the design, from the point that you have chosen how you are going to implement a certain component into your own application. From that point, the security of your software starts. And you can use a simple wrapper. When you want to expose into your software a subset of the functionality provided, you can use the adapter. When you need to convert from the provided interface to the required interface. And you can use a facade in order to simplify the interaction between a complex subsystem and your own software. And probably most of you are familiar with all of these, but the reason I'm pointing them to you is that there is a close connection between a good design pattern and the security of the software. And that's what I would like you to take away. So we have discussed by now of quite a few security controls. So the next question is, how often should we implement this into our software? To answer this question, I'll go through a real example. Rick Rescorla was a US Army officer of British origin born in Cornwall. After the Army, he decided to move into corporate world and worked as director of security at Morgan Stanley in World Trade Center. From the moment he moved in World Trade Center, he was aware that the building posed unusual security risks, partly because of its sheer size, its symbolism, the best known building in New York in the world. And he wanted to better understand the type of security this type of building would pose. Together with one of his ex-army friends, they started walking around the building. When they got into the basement, where there was a parking, the garage, the doors were wide open. There was no security guard. The trucks were coming in and out as they pleased. And they saw that as a weakness into the overall security of the building. He filed a report, and evidently the management ignored it. Does it sound familiar? On February 26, 1993, terrorists detonated a bomb truck in the basement of World Trade Center. After the attack, he warned again. They cannot come from the basement again because now it has huge doors which are closed. Next time will be by air. Because the first time he was right, the second time the management believed him. The contract lease ended in 2006, and they wanted to stay there in the building until the contract lease would end. But they agreed to implement any recommendations that he would suggest during this period. And because for him it was not a matter of if there is an attack, but when there is another attack, he wanted his people to be prepared and safely exit the building. For this, he implemented regular emergency evacuation drills, and he wanted everyone to participate into these regular emergency evacuation drills every 3 months. Of course, there are senior management that complain. They're in the middle of an important trade, and what this meant for them, it meant to put the phone down and then go down the stairs, 70 floors, like 70 floors down the stairs to safely exit the building. So yeah, there are complaints, but what he managed to do in the end was to change the culture at Morgan Stanley and have everyone participate in these regular emergency evacuation drills every 3 months. On the day of the 9/11 attack, all but 6 of the Morgan Stanley employees have safely exited the building just as they were trained. Among the casualties was Rick himself and other security officers. But Rick's well-rehearsed and consistently practiced evacuation plans have saved the life of 2,687 people on the day of the 9/11 attack. So let's go back to our software, because today the software is not only for websites, simple websites anymore. We actually develop software to power airplanes, software to power cars, complex medical devices. So it is becoming a critical part of our own life. So how often should we do these security controls? Every time our application receives input from a wide variety of sources, we must validate it to effectively reduce the attack surface in the software. The validation should be done at the entry point when the data first enters the application. Any exceptions should be logged to give the software the mechanisms to respond in real time to these possible identified attacks. Any outputs should be contextually encoded, and any time we store data into the database, we should parameterize the query to separate the data from the actual SQL command before sending it to the parser. If we need to use an operating system command, ideally you'd not use it. But if your application really must use an operating system command, we must parameterize the data, again, to separate the input from the command. And every time we bring in another component, not only open source, but also vendor APIs, we should choose a software design pattern that helps us to reduce the attack surface and enable us to get into the control of these components to easily upgrade them or even replace them if they have become obsolete. Whenever we store data, we must store the encryption keys away from the encrypted data in dedicated key management solutions. And every time we transfer the data, including behind the firewall, we should use a secure channel, TLS. Now, what I would like you to take away is that rather than focusing on these CWEs, these software security weaknesses, which we can measure only at the end after the software has been developed, which is way too late. Instead, we should choose to focus on the security controls that prevent them. We can start looking if we implement them correctly, and we can use this from the beginning into our own software. What we need to do is just like Rescorla, we must change the culture and implement this in a consistent manner every single time in order to effectively protect the software. We have to remember that an attacker needs only one flaw in order to bring down a system. That's why defending it is much harder. So we have to defend everything, and we have to implement this on a consistent manner every single time in order to make it as difficult as possible for the attackers when they try to attack a system. Also, it is important to verify that, one, we have implemented the security controls, but then we have implemented them correctly, effectively, to effectively prevent these security weaknesses. And if you want to have a further look when you go home at the end of this conference, you can have a look at the OWASP Top 10 proactive controls. There are more there. Another control is the digital identity. That's an entire talk on its own. But you can also have a look at the OWASP cheat sheet series, and these are specific techniques for certain things that you can actually look at for various technologies, quite at the point. Thank you very much.